My name is Eva Deelman. I'm a research director at the USC Information Sciences Institute and also a research professor in the computer science department at the University of Southern California. And my role in scientific computing is to look at and develop algorithms and tools that can help scientists design the computational problems and run them or execute them on distributed and high-performance computing resources. In my opinion, scientific computing plays a very important part in our lives. It basically allows us to solve very challenging problems using computation data that's available to the scientists. And there are a number of different examples of that. So you can imagine, for example, the scientists that use computing or scientific computing to predict climate change. Some scientists use scientific computing to look at earthquakes and how they propagate through the geographic area. And there are many, many such examples of using computing for science. There are many of them. However, because I live in Southern California and I work in Southern California, I'm particularly sensitive to the work that's being done by the Southern California Earthquake Center, looking at how earthquakes propagate through our geographic area, and then using this information to help design new building codes of how buildings should be built to withstand the earthquakes that are being predicted in the near future or the longer term. So I think this is something that directly impacts not only my life, but also lives of other people that live in this area. And so I think this is a very challenging and interesting problem to work on, how to make computing available to these earthquake scientists so that we can support the execution of these complex models that they have that deal with earthquake propagation in our area. One of my favorite tools, and here I'm very biased, is the Pegasus workflow management system that's being developed in my group at the ISI. And so Pegasus allows scientists to describe the computations at a high level, looking at individual components that are part of a computation, so individual codes, and how they take data in as input data and generate new data products that are being then fed to the next computational component. And Pegasus allows scientists to think about these things in a very abstract way, not worrying about where the computations are going to be actually executed. And then, so Pegasus takes this high-level description and maps it onto the resources that are available to the scientists. So it could be your laptop, it could be your campus cluster, or the cloud, or some other resources that are available in a way that's seamless for the scientists. So it takes care of managing the data movement, the computation, so that the scientists can focus on the problem, the domain problem, rather than how to deal with individual cyber infrastructure that's out there. One of the challenges that I think is very interesting comes from LIGO, which is a gravitational wave observatory experiment, which early on this year discovered the gravitational wave or confirmed the existence of the gravitational wave. And this is a very interesting project because the scientists are distributed around the globe. So you have scientists in the US, in Europe, and Japan, and other places. And also the data is distributed. So they have instruments at 2 places in the US, but they also distribute the data worldwide. And the computing resources are distributed. So they have resources that are available for the collaboration. They have their own clusters. They also have access to the national cyber infrastructure, such as the Open Science Grid and Exceed. And so they want to harness all this data and the resources to do their discoveries. And so I think this is a very interesting and technically challenging problem, because you want to be able to make use of these resources efficiently. You need to access the appropriate data. You need to coordinate all these computations and data access. And this is something that we worked on with our Pegasus tools, and we supported their computations during the discovery phase. So some of the challenges and opportunities that we see in my area is the harnessing of a diversity of the resources that are becoming available to the scientists. So traditionally, maybe they had the workstation or campus cluster. Then we saw the kind of national infrastructures coming in, such as, like I mentioned, the Open Science Grid or Exceed, which make available different clusters spread out around the US to the scientists. Now the landscape is changing even more, because you have clouds that are coming in, both commercial and also academic clouds, that are now available to the scientists as well. If you add on to that the clusters are changing within themselves, so the architecture is changing, we have deep memory hierarchies, you have more processing power. And so how do you harness all these resources and make them available to the scientists in an easy way, right? So they don't have to actually worry about how these different systems look like, where the data is located, which system is better for them to execute on. So how do you support scientists that are really interested in solving their domain problems with the infrastructure and tools that allow them to harness whatever is out there? And I think that's a challenge going into the future, making it easier to leverage this type of technical solutions. The advice is to work closely with scientists so that the solutions, the algorithms that you develop, or the tools that you develop are tightly knit to the problems that the scientists have. So really understanding what are the computational problems that scientists deal on day-to-day basis is an important part of developing things that are relevant now and also in the future.